Good afternoon, everybody. Howdy. Just real quick, I gave this talk as a practice about 3 weeks ago, and there were some common questions that came up I thought I would address before I jumped into the slides. Real quick, my name is John. I do not know what internal CTO means either, but I typically help organizations build security practices, and I help them with remediating their architectural problems. One of the most common questions that came up is, what is this? Yes, I am going as a 70s porn star for Halloween. And second, the question was, are you here just to sell us your custom fabricated, really silly password storage solution? No, the reason I'm here is for Movember. If you don't know what Movember is, it's a charity thing where you shave your whole beard, mustache, whatever you got, and you grow it back in whatever style you want. I was thinking Burt Reynolds. And so I created an OWASP team, misplaced stash. So it's for a good cause. It's very exciting. So I encourage you to either donate or participate. This is my advertisement. If you look at me during the presentation, you'll be reminded to sign up. And yes, I feel silly. Okay, this will likely become a dialogue. Feel free to ask questions along the way. First and foremost, I want to raise the level of discussion we're having about storing passwords. In general, to me, password transfer over the web and password storage is kind of like riding a motorcycle. It's intrinsically not safe. It's not the right strategy if you want to be safe. But if you insist on riding a motorcycle, we should probably give you some sort of body armor and helmets. This is not really a conversation about what body armor and helmets you should wear. There are various brands. But I want to elevate the discussion, and in particular, since I've talked about threat modeling so much, elevate the discussion in that regard. Let's look at what's actually happening with the primitives we're using. Let's look at how they can be attacked. And regardless of what you do, make sure that you can defend your position, get it past your architects, and make sure when and if your passwords are stolen, that you can deal with that situation. So that's what this is about. I'm a firm believer in history, understanding where we've come from and how we're here. We started really getting wound up about passwords circa 1973, which was before I was born. And we were using DES. And what's interesting about DES is that it was modeled to try to drive through a few iterations about a 1-second execution time in terms of real calendar time. And so we're going to see this meme propagate through 2012. We stored these passwords in etc password. We had one-way encrypted them. And we made this file world readable because we wanted, when the users to log in, their UID to be able to check that the password was correct so we could log them in or deny them. So all of you ought to be able to blow through these slides. What is wrong with this particular scheme for storing passwords? Other than the fact that Nicki Minaj and Bobcat weren't alive then either. Just shout it out.
You're right.
Oh my God, there's tons wrong, right? But if you look at my password hash, where else do you see it? Sorry, it's not a hash. It's root, and so what does that mean? They're the same. Oops, I don't have animation anymore. Outstanding. So that means that our passwords are the same, and that means if I read this file, that I can log in as root using my password. This is a problem. And that brings us to 2012. What do we see here? This is Yahoo's stolen file with some modifications. And honestly, it was this file that caused me to create this presentation. Because there was some internal chatter in my OWASP chapter, and there was some internal chatter inside of my company, regrettably, saying, well, these are salted. You can see the salts out front, but the salts are different lengths. That's weird. Is this SHA-1? Is it something else? What's going on? So what do we see here? What do you think this is? How would you figure out how these passwords are protected? How many are LinkedIn members here? So yeah, my friend, he works for Northrop Grumman. He said, you know, the real discovery here is that, you know, 5.4 million people use LinkedIn. That's the real. So I have a LinkedIn account. So what I did is I took my password, I SHA-1'd it, and then I grepped this database for it. And what I did is I grepped the database for it basically with the chunk behind these 5 characters. And what do you know? I found my hash with the prepended 5 characters. Now, why are these 5, is that assault? The answer is no, it's not assault. But what it is the testers that broke this took the weakest passwords, those that were the most easy to brute force, and prepended 5 zeros to them to protect the victim. So what that meant was that my password was very easily cracked, which it wasn't password, but it was roughly similar. It should give you a feel for how much I value my LinkedIn account. So this is what happens when you work for a company for 15 years. You don't apply for jobs very much. So in the news, LinkedIn, IEEE, Yahoo, it was fascinating. On my way to discuss this in my OWASP chapter, the Wall Street Journal called and was like, do you have any quotes for the Yahoo hack? And I said, what? No, don't. So it literally, every time I have talked on this topic, except for today, there has been a break. And so, you know, to me, this kind of indicates that your passwords will probably be extracted. Now, whether or not it's publicized, that's a different question. But I think when we architect our systems, we have to come to the conclusion that we need to be resilient against this kind of theft. Protecting ourselves and preventing it is probably going to be more challenging than we're cut out for at the moment. So step 1 is try to protect it better than these guys have. So don't be on the cover, the cover of some magazine. And 2, perhaps more importantly, if your passwords are stolen, make sure you have a great story that you can deflect this problem. So being who I am, I went ultra sort of pedantic on this and created a 38-page threat model, which is a Google Doc, which is available to anyone in the OWASP domain. I broke it down into 2 different sections, stealing and acquiring the database of passwords, and then breaking those passwords, however they're protected, and reversing the actual credentials out of them. I ordered the attack vectors by difficulty. I created threats of various different types. T1 is the classic application security concern, internet-based threats. There are victims, there are hapless victims, targeted victims. There are men in the middle, T2, and then there are insiders, T3. This is terribly uninteresting. We're going to get to the meat of it. But if you want, Friday's coming up, you can get a bottle of wine or a bottle of scotch, whatever your pleasure is, get these 38 pages and cry yourself to sleep. The current industry practices really haven't changed that much since '73, to be honest. We've used different f of x, but the f of x's are very similar in nature to 2 forms. And we still, when we do assessments, see all of the things listed here: plain text, encrypted passwords, hashed, salted and hashed, adaptive hashes. What I found when I started talking about what you should do is that people didn't know what the cryptographic primitives do. It's a doo-doo. And so I thought that there was an important primer in understanding the properties, the security and privacy properties of the primitives, because without that, we're going to have a shouting match about whether you like your religious solution or mine better. And so we need to go through the properties of a hash. So what are some properties that hash functions have?
One way.
I'm sorry, they're one way. Man, diffusion is what that's called. Small changes in the input create large changes in the output, and that's the last thing on here because everyone forgets it. Others?
Those are really fast.
They're lightning fast. I don't want to get into that. They should be collision resistant. So presumably, hashes are unique on the output space. Presumably, they're deterministic in terms of the transform. So A will always hash to the same value, B will always hash to the same value. And that those transforms should be collision resistant. In other words, no A and no B should collide with the same output. They should be non-reversible or one way, which was the first thing that was said. They should be unpredictable. So if I add like 1 or mask the input, you know, I can create some of these properties, but it's predictable. And then diffusion. I actually don't have speed on here. That's outstanding. There we go. They're lightning fast. And so this is the problem that really gets our shorts in a bind regarding protecting passwords with this, right? Because if we have a one-way function that has determinism and collision resistant, all of these are great ways to store and protect a password. But if you have a password dictionary, you can run the function in a lightning fast fashion, and then you can brute force the space and reverse the password. So we don't like hashes, naked hashes anyways, for protecting passwords for that reason. So that's pretty straightforward, right? Go on. I guess we're done here. Woo! Yeah. Do the arrow the right way? Right. So is the solution just to use a better hash? We can go to SHA-2. There's various different forms of that. We just came out with SHA-3. Is this the answer? No. Forever. Yeah. No, this is not the answer. So what property in the last slide do these hashes affect compared to the SHA-1? Collision resistance. So they have a larger output space, and so in theory, with the fixed input space, there should be less collisions. But was this the problem we had on the last slide, or was it the speed? It was the speed. So this doesn't solve the problem. Now, it's okay if you thought that this was going to be a fix. I'm surprised at how many people think about this. It's not the fix. And so I think it's valuable. If you understand hashes, that's fine. This last slide was a waste. But regardless of what cryptographic primitive you're using, it's important, I think, when you're evaluating as a solution to a problem, to write out those properties explicitly and consider how they're going to affect the security and privacy issues of what you're attempting. So the question then becomes, okay, so this is how people are storing this stuff. How can we attack these problems? So as I typically do, I believe that is a threat model specific question. So I broke this down into 4 classes of things. 15-year-olds at home in their boxer shorts, application security professionals such as ourselves with a decent toolkit for attacking, well-equipped attackers, people who can do GPU and FPGA acceleration, and then people who can do all of those things and have an acre of CPU to throw at it. So the nation state or the well-equipped concerted threat. We're going to focus most of our time on the middle 2 because the top one is really boring. And the bottom one is almost impossible to defend against. Also, some of you are probably in the business of protecting against nation states. Many of you are not. If you are in the business of protecting against that, you probably need a solution that I cannot simply present to a group this size. Yes?
The claim I hear is an S-script because it takes up so much memory and defeats all the massive parallelization that's possible in nation state.
It is indeed the solution to all problems, and last weekend I had it actually tattooed on my left arm. So that's later. I can only rip this once. That is where I tattooed it, but I described an alternative location for the bcrypt tattoo. That's correct. So, what was the original guide? Doesn't scrypt solve all these problems because it's memory hard? It is also CPU hard, but we will get to that. We will get to that in a profound and gory detail later. Okay, so what attacks do these people have available to them? If you remember the attack vector slide, there's basically dictionary attacks, fully exhaustive brute force attacks. The next kind of attack is a rainbow table attack. And these are attacks that an AppSec professional may not know today, but can go to things as lame as Wikipedia and drive through to completion in about a week. The net of all of these attacks is that they trade off one of 2 things: speed, or CPU, and space. So you have 2 choices once you steal the database. You can plow through it with CPU and try to break it, or you can do that over time before you steal the database, and you can look it up in a table. I have hidden slides that talk about the size of the brute force tables. If you want to see, there's like 30 slides in this presentation. There's like another 30 slides hidden that go through other footnotes and other sizing or speed requirements. We've done a lot of testing on this because on the mailing lists and so forth, people throw out all kinds of things like you could never break this, you need this much space to break this. Most of what they've said is wrong. So we've done the research, footnoted the research, and then threw it in here. Most of the time we haven't done it, we've relied on other people who've done it. So, but I think rainbow tables are particularly interesting to talk about because almost everyone I've heard talk about them in this space has totally misinterpreted what they are. So a rainbow table is an attempt to combine this space and speed trade-off in a single tool. So if you're going to exhaustively look at passwords that are extremely long, particularly longer than 9 characters, and then have a variety of dimensions to the character sets that can make up those characters, it's going to take too much space to hold them. So a rainbow table is basically a hash chain scheme, and if you're interested, again, that's another great bottle of wine Friday night activity, that basically allows you to chain the hashes together so that each you may have to try multiple times to get through a single chain, but you can save a lot of space in holding the whole table. And so the colorization of this is a little bit confusing, but basically there are dictionary tables for particular operating systems and the protection schemes as operating systems use, and this describes the number in terms of space that they require for each of the dimensions in each of the password lengths. I'm sorry, go ahead.
Yeah, many tables say available for SHA-1. Are you aware of tables for SHA-2 and stronger?
So in fact, when so the answer is yes. And in fact, when I SHA'd my LinkedIn password, I also Googled the hash, and it came up it was a Russian site, but it was a dictionary. So I could have reverse looked up that stuff, and I didn't even have to use my disk. It was someone else's. Now, interestingly enough, Vista.
What was the original?
Oh, I'm sorry. You've asked that twice, and now I'm not going to screw up ever again. I'm going to repeat the question. So the question was, what was the question again? So he got this. It was basically there are hash tables. I'm sorry, there are dictionary tables and rainbow tables available for SHA-1. Are there tables available for other things? And the answer is yes. In fact, this is from Offcrack, and I have all the notes in the slides and URLs. But basically, if you look at Vista, Vista does not use a SHA-based scheme. It's a different scheme, and these are rainbow tables available for that scheme. Outstanding. So this is the same thing in text, which is redundant. So the next thing we think to do after we hash is that we salt. And so what does the salt do for us? Well, the salt solves the problem on that first slide, right? It deduplicates the same passwords stored as either ciphertext or hashes. And this is interesting. It's caveated here because this is important. It increases the entropy required to drive through the brute force space, but only if you're looking at the whole password population. If you're going after a particular user's password, it does nothing to increase the entropy. Why? Because the salt, by definition, is prepended to the digest text, and if you've stolen the database, you've stolen the salt. You pull it off the front, you run your calculation with it. So it's valuable to increasing that time because it forces you to do the online CPU-based thing as opposed to the stored attack. But it also only really prevents you from brute forcing the space if you've got a population.
Do you think of techniques like salt isolation, where you put half the salt in the database?
I have 3 slides on that. Absolutely. So what's fascinating to me is that when I look at real-world production systems of Fortune 500s, I'm surprised at how infrequently they salt their scheme. And so I'd like to introduce you to this notation, which is standard or non-standard, depending on your point of view. Prepend the salt to the plain text, throw it through the hash function, and store the digest with the salt prepended to it. So outstanding. It's a little bit non-standard. So can the salted hashes be attacked? And I just went over this. So if you jack the database, you can do a CPU-based run on one user's password because you have the salt. If you have to plow through the whole population and the website has more than 10 users, then the population and the differences of the salts for each user will probably prevent you. Some organizations have gone to a salt-based system, but they've used the same salt for every user on the site, which I'm excited by because that has nearly precisely zero effect. It does have a slightly positive effect in as much as it does invalidate the previous rainbow or hash tables, but they can be recalculated relatively quickly. And so what we're going to start to do is we're going to start to look at what a well-equipped attacker can do and how we're going to prevent them, because we've kind of gone through the some guy application security professional, and I don't want to spend a lot of time on this slide, but I want to show you it. Basically, the gist of it is with a few $100s, you can bang through relatively commonly length passwords, 8 or 9 characters, in a relatively short amount of time. And this is with garden variety graphics cards, which, in case you're not aware of how these work, they typically have between 160 and 320 parallel processing units on them. So just suffice it to say that most of the laptops that you guys brought can try between 3 and 6 billion SHA-1 digests per second. And so when you think about dictionary or full space brute force attacks, I think we can conclude relatively easily that those kind of hashes are insufficient to handle the problem. So let's move on to my tattoo. So the solution to this problem was the adaptive hashes, and these are algorithms designed specifically to avail themselves of all of the positive properties of hashes, but remove that lightning fast thing, okay? Because that was really what was causing us the burn. And this thus protects us from both brute force and these kind of table-based attacks, because each password attempt that the attacker makes is moving back up towards that 1 second that Des originally took when we logged into our Unix box in 1973. So these approaches do this by iterating the hashing function. And they do other really interesting and fun things, which we'll describe superficially here. If you would like to discuss further, we can do that, but I'm going to need a bourbon. So the first such adaptive hash is PBKDF, PBKDF2. It's a family. Again, all of the resources for this are here. This is simplified. It's in red. It is all caps. I imagined, I almost did an exclamation point. It's simplified. It's simplified. This is not the exact algorithm. I'm not claiming that it is. Okay, we got that? So what basically this does is you get a salt, you pick a C, which is the number of iterations at your work factor. You pass the salt and the password to PBKDF. You also pass the output length that you want. And you get a protected password back. You store that with the salt appended to it. How does this work? This is simplified. This is not the actual algorithm. But you basically run this thing in a loop, and then you do some fancy things to mix the blocks together, because that provides you very advantageous properties to prevent more interesting cryptanalytic attacks. We're not going to talk about the more interesting cryptanalytic attacks because we're only focusing on that well-equipped attacker, not the concerted nation state. So the problem with this function, if there is one, is that we have to pick a good C. So we have to basically size this thing. So NIST says 1,000, iOS 4 uses 10,000. It's been said that it requires 10 million to be secure today on modern hardware. That's an open question, and you've got to work that out if you're going to use this function in your environment. Okay, so there are positives and negatives to this, but we'll get to them later. The advantage to one more thing to say about PBKDF before I move on to the other adaptive hashes. The spec is slightly ambiguous on this topic. If you look at the body of the spec, it says you can use any PRF. In this case, you see it's SHA hmac. In the appendix of the spec, it says you can use any. So some people you will talk to about PBKDF say, well, you can use SHA-2, and that makes it better, and they'll end up with a variety of arguments. If you use the JCE, it does in fact have a generic implementation, and then in the call to the function, it goes ahead and checks the string to see if you're using SHA-1, and if you're not, then it throws an exception. So the reality is, regardless of the spec ambiguity, most implementations hard code SHA-1. So that's that.
So, how serious it is like low-grade caches is used in this password-based encryption? For example, speaking about JC, I didn't see SHA-2 digest available there. Those they have a same MP5 or something.
They have, the SHA-1 is hard-coded into Java 5 and beyond. So
They definitely don't have much bouncing castle probably.
that's correct.
How's the big risk of using low-grade?
So the question is, what is the effect of the security of using a low-grade hash when you use these rounds? Presuming the answer is, well, the answer for the concerted attacker is if you have a problem with the distribution and output, the diffusion property, then you may be able to do special interesting attacks. Most of these functions that are implemented prevent things like length extensions and things of that nature. A lot of the security is coming from the C, the work factor. So to the threat we're talking about, it's mostly just picking the right C. That is not strictly speaking if you have someone who has some cryptanalytic capabilities. I would push this onto the stack and we can talk about it afterwards because it is an interesting concern. But we're going to move on for the sake of time and you can harass me about that. Absolutely. So if PBKDF is not the answer, then perhaps it's bcrypt. And there are many people who feel immensely passionate about the use of bcrypt. Bcrypt has a similar interface to PBKDF2, but under the hood it's very different. Whereas PBKDF is basically an iterated hash function, this is actually an encryption with a CPU hard key generation scheme. And so what you see is that what it does is it takes a sort of basically a known plain text here at the bottom, and it uses blowfish to a particular work factor expand a key, and then it encrypts that key, this known plain text with that derived key. One of the big differences, other than this structure, this is much more like DES in structure than the hash-based PBKDF is. One of the differences in this is that the work factor in PBKDF is linear. The work factor in bcrypt is exponential. So when you increase C, you get more bang for your proverbial buck. Another interesting difference in bcrypt from PBKDF is that it returns a structured output, which is interesting. It appends the work factor, the salt, and the digest together so you can store that. And there's tremendous value in doing this. When you prepend the work factor to the digest, if the application server goes down, if the developer is hit by a bus, if any number of things happen, you know how that thing was protected, and you can attempt to verify it later, even if that because that information is recorded here, whereas that is not the case here. So there's some argument as to whether or not this cost is enough at base, or what the right cost is. This is certainly not supported by the JCE. That is a huge problem for my customers. And another problem, oddly enough, is that they don't want to use blowfish either. And so, you got to download it from some guy's website. And certain organizations don't want to stand for that. They want it in the JCE. They want it supported, and so on and so forth. It does mostly resist GPU parallelization, though that is falling apart, but slowly. But it certainly does not resist FPGA parallelization. So a lot of the argument between bcrypt and PBKDF, honestly, because you can adjust the work factors to be equivalent, is basically the support you get in your either Java or .NET packages. So almost all of the pushback I've received from using bcrypt in production environments is the support. So if you don't have that problem, this may be a lovely option for you. scrypt is bcrypt++ in as much as bcrypt++ was, or PBKDF++ was bcrypt. scrypt adds a few more factors. Let's not talk about R. It's basically internal block size, but basically scrypt allows you to adjust the CPU hardness of the algorithm, but also the memory hardness of the algorithm. And we can talk about that afterwards if you're really interested. The scrypt paper is absolutely something you should attempt to read and understand. It is rather difficult as compared to the others. This is a tragic oversimplification of it. But basically, the gist of it is that it does really fancy things to set up a matrix and really mix the output of another adaptive hash, PBKDF2, together and use a profoundly larger amount of memory. If you know anything about GPUs, you can store it in the registers, you can store it in the local memory, which is about 32K, or you can go out to the PCI bus, and that is just, you know, orders of magnitude slower. And so scrypt really succeeds in trumping both PBKDF and bcrypt in terms of its ability to resist parallelization. To your question, Jim. There's a good paper on that. I have both of them listed in here as links and at the end. I was thinking of a metaphor for relating these. I'm going to leave it alone though. So what are the properties of these? Why would you use them? Well, they resist most threats attacks, except for the nation state attack. So I think that's probably good enough for 99.99% of the population. They're very simple implementations. You saw the APIs for these things. You download a jar, you download an assembly, you get a library off the C compiler. You basically call one function, and lickety split, you're there. And that's good, that's great. They scale CPU difficulty with a parameter, but we struggle to figure out what that parameter is. So there are some limitations to this as well. Remember I said that there were three purposes. We want you to be able to articulate what you're going to do. We want you to be able to get it past your architects into production. And then when you get busted, you want to be able to be resilient against that attack. So my experience with architects is when you sit down and explain to them that you have a solution to the problem, and it's to do something very similar to the former solution, but do it 10 million times, you have just slipped into the definition of insanity, which is doing the same thing over and over again. And while it's perfectly valid to increase the work factor, it's sometimes a challenge to articulate. Also, this can create a problem because of the lack of the support in the toolkits in heterogeneous architectures, where you don't have availability of the APIs. And in fact, scrypt is sort of increasingly less supported by implementations that have been well vetted and have gone through all the test vectors than even bcrypt. Just because we can play with C does not mean we have the ability to be resilient. So imagine this. You set C to 1 million. You think you're good. You throw the stuff in production. The database gets stolen. Your plain text passwords show up on the net. What do? You can't just change C. What does that mean? You have to change C in development, promote that stuff through. Some of you are very agile. That'll happen quickly. What do you do with your production data? Do you basically set up the equivalent of a brute force attack, tear through your database and iterate this stuff? Do you have to set some sort of block in your login code to make sure that you're checking against the previous hash scheme or the current one? So the most important thing, honestly, you can do to have a good story, as far as I'm concerned, on password storage is be able to deal with the eventuality that it can be stolen without having to make code changes, design changes, and then database changes. So this C thing seems, when we think about it as a security guy or maybe just a sort of a unit developer as a solution, but there's much more to it. The other thing is that I think we need to obtain, in addition to the fact that I don't want to do the same thing over and over again and call it a solution, I think we need to obtain asymmetric warfare in order to declare success. So if I'm using bcrypt or scrypt, I'm costing the attacker 1 second, 1/2 a second per try. But I'm also costing my servers that much for every user that they log in or every user they unsuccessfully log in. And I don't like, personally, this is just me, any solution that costs me as much as my adversary. Because, I don't want to be in a cat and mouse game. I want a situation under which I am paying a small price as compared. And I already talked about number 4. So let's look at what the defender versus the attacker really means, and let's look at this asymmetry, or how we can produce asymmetry. This is the crux of it. This is the most important thing with respect to architecting the solution, in my opinion. So the goal for the defender is to log in a user without spending more than a second delay. Now, the attacker has a very different goal, and this is very hard for some security guys to understand. They may need to crack only one single password out of the whole database. So LinkedIn, these password databases were on the order of 7 figures, small 7 figures, 2 to 5 million. But they only need to crack one of them. Now, if you're going after a particular user, like the admins, then you may have a more difficult task. Or they may be trying to break 10 of them, like in the case of LinkedIn, to have a media event. But those are three very different average and worst case break times. And so we have to think about that within our threat model as we compare the solutions. And the solutions will, in fact, compare very differently based on those objectives. So the way that scales is based on rate and burden. So one of the clients I'm working with has 55 million users, 20 million active users at any time, 2 million active login attempts successful per hour. So that isn't a lot or a little, but it's what they have to support. They have 4 to 16 CPUs per application server, and they have 2 to 64 servers per retail banking portal. In this case, they have 8 CPUs per server and 16 servers in their deployment. So the success gauge, as far as I'm concerned, is when we change their SHA-1 implementation to another implementation, like an adaptive hash, how many more machines are they going to have to buy and deploy? Because I'm going to cost them more CPU, or more memory, or both. So the attacker has a different arc, right? So the attacker, they can scale their hardware with the value of their prize that they break. And really, their burden is that they're bounded by, they have unlimited time to do the break. They're bounded by how long it takes the users to reset their passwords. And if they don't communicate that the password database has been stolen and the organization has no ability to audit and monitor that, that could be truly an infinite amount of time, depending on the password reset policy. So, what we have is a situation in which a population of 20 million users divided by 2, if I tear through that thing, I ought to be able to get a break on average in about 10 million users, worst case 20 million. So my success gauge here, but I have different hardware with which I can do that. I have FPGAs and GPUs. So the success for the attacker is how many days it takes to pop the password. Yeah?
Is that the right measurement, though? Because I can parallelize so much. Is it really days? Like, can you say more about financial costs?
It would be if I couldn't do this with commodity hardware to some extent. So people have done some really, and they're in the notes of the slide, some analysis on how much it costs to do this with Amazon. And Amazon is particularly cost ineffective to do your password hacking because their GPU time is so much more expensive than their CPU time. I had a machine at home with 3 graphics cards, and I was perfectly constrained by the speed of my PCI bus, which is only 169 gigabytes per second. And so I literally could not feed passwords from my file to the GPUs to break them fast enough. My PCI bus was throttling it. So but you can make slight modifications to that hardware scenario into your code to overcome those problems.
Even better, it's going to take me 30 days to crack a certain password with one piece of hardware. It should take me 15 days, so I split the problem in half and just use.
And it may cost you twice as much, but you can control that cost variable. So to me, and you could argue either way, but to me the barrier is, if I use commodity hardware, a good application security professional has a decent machine, let's say $10,000 worth a year, right? So, the average defender has what I'm describing here. So I'm just going with averages. Now these things can scale up or down. Here's what's interesting. These are variables. So I created a spreadsheet to describe these variables because you know what? Your attacker is going to have a particular set of capabilities. And your server farm is going to look different. And your user base is going to look different. So these numbers are just my client. Okay, so your numbers will be different. So I thought, well, the best thing to do is create a spreadsheet and give you guys the spreadsheet, and you can run the numbers. And you can set those values equal to whatever you want. I don't care. So what I did was I thought, let's go back to 1973. So let's target this thing for 1 second. Okay, and I put all of those factors on the previous slide in, and this is totally fascinating. So we can argue about whether or not I can do a bcrypt round in, 1/10 of a second, or the bottom line is that I can do it about twice as fast on a GPU as I can do it on a CPU. So I worked that work factor into the 10 million population and the average thing. And so what I came up with a graph of both of these things, the attacker and the defender. And what I found was at 1 second per bcrypt login, it would take 35 machines, not 8 or 16, to accomplish login at full CPU load, which of course these authentication machines are doing other things. So I'm a bit concerned about that. I'm really asking them to make a big change to their production environment and really scale that up. What's interesting about this is that the same 1 second for the attacker with this commodity hardware, 2x on the GPU, again, home-based systems, is less than 60 days. So Jim is a baseline with commodity hardware. The inflection point is interesting. At a second, you have, I got to buy 32, I got to buy 24 more machines for my customer, go through burn-in, that's 3 months, by the way. Go through testing, it's another 3 months. I'm 6 months away, and 24 more machines away from the solution, and 3 months, 6 months. The attacker is 55 days away, right? So I have not achieved asymmetric warfare, and I have made no onerous assumptions in making this trade-off. You can make as onerous or as aggressive assumptions as you want in this spreadsheet. So I don't like these adaptive solutions naked because I don't think they provide asymmetric warfare, and I think they have a particular problem, that iteration count, that, again, naked on its own, is going to cause me with my architects. If you're using bcrypt or scrypt or PBKDF2, that's fine. You need a good story to explain it to your organization. I'm not against them. I'm not for them. I just work here. Yeah.
I do see a lot of organizations moving to bcrypt because a lot of people recommending it, and I find out that they're using a work factor of 1 or
Very
a work
common.
factor of 2.
This is a work factor 1. But remember, the work factor is baked into this calculation symmetrically. So if you change the work factor to 10, both of these numbers are going to go up. And so what you have is it's going to take 1.4 seconds to log in, which means you're going to need 45 machines. And what you see is that you go to 1.4 and it's going to take 70 days. So it's baked into the calculation. Pick what you want. I mean, smoke your own. So I think that there's, we can go back to threat modeling and we can go back to security architecture, which is my favorite saw. And we can start to use other properties to come up with different solutions. Are the solutions better? Yeah, actually, they're kind of in an equivalence class, but they have different properties from an architecture and from a maintenance perspective. Let's look at defense in depth, let's look at compartmentalization, and let's look at separation of privilege. I believe that adaptive hashes are the best to strengthen the system with a single control. I want to pause on that because people often say I just bash them. But I think we can do better with defense in depth. So we can use something like an hmac. Now, what is the difference between a hash and an hmac? It requires a key, which is going to, if we protect that key, presumably, talk to the identity of the person who computed the hash. You're allowed to heckle me, but other people have to give me solution answers. Wow, there you go. So, I was gonna say you're not really trying out for the thank you for the big leagues with that one. Okay, so right, the motivation for using something like that is it does inherit the hash properties. The best hash property that hmacs inherit is the lightning speed. So we're getting the advantage back on the defender side. Outstanding. So, but it resists the threat's attacks because it provides this additional search space in the key, which is additional entropy to someone brute forcing a single password or the population. Here's the other advantage. It requires you to pull stuff out of the database, and it requires you to pull stuff out of the application server. So now I'm forcing them to attack the database to pull the passwords and attack the key store. So are we done? We can just go home. This is easy. Just do this, right? Well, there are trade-offs. Protecting the key material really challenges developers. I can't really say that I've gone to an organization and be like, you know what, you got key management down, and so we're out. In fact, one of the things that Tom, last time I gave this presentation, said was the most common place for the developer to store the key is in the database, at which point the compartmentalization has collapsed and I've got nothing. Yeah.
What about network HSMs?
What about network HSMs? So I think there's a role for that kind of, what about network HSMs? I think there's a role for products like HSMs to play in helping developers protect keys. I'm pumped about HSMs because anytime I can explain to the architect that there's a security product that they can buy to help with the solution, I tend to grease the wheels, even though I'm not a product guy. And that's slightly...
Doesn't that just push the problem once you have to have a key to get the HSM?
So it does push the problem, and it pushes it in really annoying ways. the way that we usually describe this is it's turtles all the way down, right? At some point, you've got to trust something. If you're storing the key in an HSM, there's a way you connect and authenticate to that, so you've got to protect that credential. And I like the fact that I'm storing my passwords in the database, and I like that I'm storing something in the application server for the following reason principally. Because a SQL injection or a backup or a tape-based attack on the database is fundamentally different than a break of the host, the key store, the HSM, or an RMI injection on the app server. And to my knowledge, I'm one of the few people that can actually pop RMI code in a remote machine, so I'm pretty happy with that solution. But there's tons of ways to screw it up by putting the key in the database, by putting the thing in an HSM and sticking the key in the code and having it popped out with an exception or any number of things. This is not a panacea. It's a way to invoke defense in depth and compartmentalize. I don't like this solution naked either, let's be clear. But if you were going to implement this solution, I think it's a good solution to implement if you're rolling with like a Java 4 or Java 5 environment and you need to use only FIPS certified primitives. Because the Java 5 environment doesn't even have PBKDF2. If you're not allowed to download and validate other jars, like Bouncy Castle was mentioned, you may be stuck with a solution like this because your policy states you can use nothing else. You still have to get other things right, and so on and so forth. So the question, Manica, was, can't we just split the digest, or put another way, isn't just splitting the digest in two morally equivalent, quote unquote, to using an HMAC? Yes or no? Have I set the question up too obviously? No one voted. So the answer is no, they're not the same. And remember the first example, right? I was able to discern that this was SHA-1. I was able to discern the scheme and find my password, even though they zeroed out the first 5. This problem of diffusion is a mother, right, for these schemes. Diffusion means that a small change in the input makes a large change in the output, which means that the collisions on even a half hash are in fact incredibly unique. So I built a password database. Well, I downloaded one. It was 2.147 million passwords. They were all character sets, so alphanumeric, caps, lowercase, and symbols. And then I split the digest in 2. Well, why didn't you split the first bit off and leave the rest? Well, because 2 is the worst case scenario. And then I ran basically a collision check on that database, salted individually and uniquely, and I came up with no collisions. On PBKDF2, salted with an 8-byte salt, and I was able to crack these things at hundreds a second. And so I have a slide in the back where I, if you want to get very excited about it, I have a slide in the back where my test data exists. You can download my code, and you can try this on your own if you're into it. Again, very exciting way to spend a Friday night. And so unfortunately, that solution is not really going to work for us very well. And that's kind of interesting, right? I've seen a lot of security guys talk about this. So then what's the next answer, right? Well, do I split it in 3? Do I split it in 4? Do I put one in the database and one in the key store and one over here on the, the file system? Yeah.
So I'm not sure if I understand that. Are you saying because you split the hash in half, that because it's so diffuse, even with just half, you were able to successfully...
When you brute force it, only compare half, there's no collisions on the space. So if you get a match, it's a unique password match. And when you try that password, it will work. Oops. Right? So, and this is like treading the line between the brute force attacks and the cryptanalytic attacks, right? And it's lowbrow cryptanalytic. But the point is that you need to list those properties out, like I said, so you can remember to test these things in your threat model or your misuse cases. I don't like solutions that split the hash and get fancy like that, because those aren't sort of approved cryptographic primitives, and it starts to smell like the property of security by obscurity to me. If you do this, it's great. I'm not here to hate on anyone's design. So there is a reversible design. And before you flip out that I've put a reversible password storage design up there, this is actually quite similar to what Mozilla suggests. And actually, I have promised to work on the password storage cheat sheet. And I have also started implementations of these things so that you can just call them and get the key store stuff right out of the box and make sure that it's not SQL injectable. And I also have I'm sharing the breaker, the breaking experimentation interfaces, so you can call those too. So this reversible design has interesting properties. Let's say that we use an adaptive hash, something like an script or a PBKDF, depending on whether or not you need it supported, and we do the same scheme we had before, and then we encrypt that with a key, with a wrapper key. So this provides us a different set of properties, and we still separate them into where they're storing them, so we have something here and something here. So this provides, this inherits all of the benefits of the previous solution, and it adds the adaptive hash slowness. This means that this has a few positive benefits. It still requires two kinds of attacks. It still requires the brute force, which is out of reach. And what's neat about this is if someone just steals the key out of your application server, because the scheme was reversible, you can just rotate that key. You can't do that with simply an adaptive hash because you'd have to interact with the user. If someone steals the database and the key, they still have to brute force through the adaptive hash. Unfortunately, there are a lot of limitations to this. They're very similar to the previous limitations. You've got to get the key storage correct. You have to separate the items, otherwise the internal threat can still bust you. And quite frankly, this takes us from asymmetric warfare back similarly to symmetric. You guys are a much less belligerent audience than the last one I had, which I appreciate, but Okay, so the most important thing I think we can do, rather than talk about particular schemes, is talk about how we're going to deal with the operational impacts of these things. I talked about C. So step one is we need a way in our design to protect the user's account. So if my database or if my keys are stolen, I need a way to block login and delete all of the shortcuts associated with login so that I can basically deal with the fact that some of my passwords are eventually going to be compromised. This may mean some sites like Facebook or your bank site may associate fingerprints with your machine, trust this machine, whatever, right? So I'm going to want to strip all of those shortcuts to log in away if my password database has been yanked. A lot of systems have those shortcuts, but no way to revoke them. I'm going to want to integrate the new scheme, and I'm going to want to use those versions that I talked about in order to make sure that the data in my database can be incrementally upgraded, especially if I use an adaptive hash. Because of those 20 million users, they're all active, but I have 30 million other users that are database that are inactive. They may not log in for 2 years. If I have to tear through all 50 and do an online fix, I'm basically subject to the constraints of the brute force attack that the attacker has to do. So I do it incrementally, so I need a way to version what's been updated and what hasn't. This is actually a really clever trick that could augment the existing Mozilla guidance and improve it. If you use only a one-way scheme, one of the ways you can update the databases it's stored is basically to wrap that scheme in another either keyed hash or adaptive hash. So if you use SHA-1 right now, one thing you could do is just decrypt it and make sure that you get the version in the salt different and correct so you can differentiate the digest texts. Now, this does not help you prevent the brute force attack because wrapping a weakly encrypted thing with a strongly encrypted thing doesn't help when the weakly encrypted thing has already been stolen and someone's brute forcing it. But it is something you can start to say, well, we've updated our scheme and we've asked our users to reset their passwords. And so if this happens again, I feel like I have a better story. Aha, when the user logs in, I'm going to need them to change their password. But because the passwords are compromised, I'm going to have to apply additional checks to make sure that it's the user I think I'm talking to. That may be out of band exchange with their cell phone. It may be secret questions and answers. It may be so on and so forth. So just nailing this checklist of things I think is really important. And in fact, like I said, most systems would be hard-pressed to implement these things in retrospect from where they currently are. I'm competing with a band now? OK, so there's a ton more content in this presentation. There's a ton more interesting gotchas and tricks underneath the hood. There's a ton more slides talking about the specifics, but I did want to keep it to an hour.